So hopefully you've received the email from me regarding the midterm exam, the actual choices you made on your booklet, and the fact that your booklet should be out in these literature racks out in the second floor corridor on the walls. So please pick up your exam, and it's something to learn from. The next problem set is due Friday, and it uses material from today, where I'll finish talking about wood stoves, and hopefully I'll start a little bit into the story of water, steam, and ice. But those two topics are really the basis for this problem set, so we should get everything done in time. I'm crunching, and we'll post water, steam, and ice after class. It's my usual state of affairs, just barely in time or not even quite in time. Well, where I left off last time talking about wood stoves was having made the thermal energy that we use to heat the room. How do you actually get the heat into the room? And I'll start by asking any questions about the idea of producing the thermal energy by burning the wood. You have any questions about that? Try to give you some idea of what a chemical bond is about and how you can rearrange things and release energy in the process, typically as thermal energy. So we've got a hot burn gas inside the firebox. How do you get the heat out of the gas without actually just sending the hot gas into the room? And the three mechanisms of heat transfer are all active in a wood stove. And so that's part why I chose the topic, is because we can watch heat flow. And I'll remind you that heat is energy flowing between objects because of a difference in their temperatures. And it naturally flows from hotter to colder, and where hotter and colder can be measured with temperature. In fact, this gives rise to the whole concept of a temperature. Temperature allows you to predict which way heat's going to flow. And so heat flows from hotter to colder, higher temperature to lower temperature. What else? If the temperatures are the same, no heat flows. And you can say that objects are in thermal equilibrium. They do not exchange heat. We'll play more with that when we get to talking about air conditioners and stuff. What else? We'll see it as possible to move heat the other way, but you have to do it deliberately. You can move heat from cold to hot, but that's a challenge. It doesn't happen naturally. One more observation is that heat flows from hotter to colder for statistical reasons. It's not the laws of motion that cause heat to go from a hotter object to a colder object. It's a statistical process. If you just roll the dice over and over and over again, for example, the casinos make money not because they're going to win every time, but because they've got the system rigged so that, rigged, or the game is built such that over a long term, lots of statistics, they're going to eventually make money. You're eventually going to lose money. The same is true for heat flow. There can be microscopic movements of energy the wrong way, but if you do it long enough that statistics begin to dominate, heat will go from hotter to colder. Okay, so how does it actually move? The three mechanisms, which you've surely heard of before, I said them last time: conduction, convection, radiation. So let's go through them one at a time. Conduction is the flow of heat through a material without the material itself moving. So just a bar of pick your favorite solid material. It can be copper, it could be wood, it could be glass. Any of these things, heat can flow through that without the material itself actually going anywhere. So if you heat one end of a rod, make it whatever your favorite material is, you heat one end, you cool the other end. So the temperatures are different. Heat will migrate through the rod from the hotter side to the colder side, again, statistically. And the starting point for why that happens is just the microscopic jostling of the particles because of their thermal energy. So in principle, if you zoom in on the end of the rod and you look, you see, oh gosh, there are atoms there. The atoms are not just sitting still. And this is a little bit of a fluffy story because atoms aren't really little balls and stuff. Life gets complicated when you get down to particles that small. But still, the concept's good, that the atoms are not just sitting still. They have thermal energy, which means that they are moving about. Thermal energy, it turns out, measures the average thermal kinetic energy of the particles that make up a material. So if at a certain temperature, all the particles, what are the particles? That's a little bit fuzzy. What are the particles is a more complicated question that I want to answer. But the atoms is a good first approximation. The atoms are jiggling around. They have thermal kinetic energy. At any given moment, they're moving, certainly on average. So they're jostling around, and at the hot end, they're jostling more vigorously than they are at the cold end. And just because of the statistics of the bumps and jostles, it's like if you're in a crowded, I don't know, dance floor or something like that, and at one end of the floor, the people are just wildly banging them around, and the other end, everybody's sitting around trying to be sedate. The jostling motion is going to work its way through the crowd, and there's going to be a net flow of motional energy from the wild and crazy set to the sedate set. Just going to migrate that way. So that happens in materials. I think of it sort of as a bucket brigade transfer of energy, where bucket brigade is the old way of putting out a fire. You'd have a whole bunch of people lined up in a line from the river to the fire, and everybody's passing along buckets of water. They're going one way full of water, and they're coming back the other way empty. And you just keep passing them along. Well, this is thermal energy being passed along atom to atom to atom to atom through the material from one end to the other. We're okay with that? That is, in any material, that process is present. It's a pretty slow way of transferring energy. So if that's the only thing present in a material, the transfer of thermal energy from the hot side to the cold side is modest. It's not all that fast. It does depend on some things like exactly what the material is. So different materials have different, handle this bucket brigade process differently. But it also depends on how far apart the hot side and the cold side are. Not surprisingly, the farther they are apart, the slower the process is. And it also depends on how big the temperature difference is. So basically, the bigger the temperature gradient, that is, if you have substantial temperature differences and they're close together, which makes a big swoop from hot to cold, that's a big gradient, the heat goes faster. So do I care about that you ever remember the details of this? No. But you should have some sense that you take I don't know, something that transfers heat decently. It happens, a piece of aluminum. You have a piece of aluminum, you put it into boiling water at one end, into your hand the other end, and they're far apart, you're going to get hot pretty soon, but not too bad. But you take that same aluminum bar and you put it into a roaring fire, bigger hot, the temperature of the hot side now is much higher, and you get the hot part close to your hand, it's going to burn you fast. The heat's going to come roaring through quickly. So just as sort of, you should have some intuition about the heat flow through materials like that. That said, the bucket brigade effect is not the dominant effect in metals. So materials that conduct electricity, they also are very good at conducting heat. And it's the same mechanism. Electricity, which is not a topic for this semester, it's a topic for the other semester. Electricity moves through materials through the movement of charged particles. In almost every case, it's the movement of electrons, which are surely something you know about. Electrons are little electrically charged particles. They happen to be negatively charged, which is one of my harangues of, this is Benjamin Franklin's unfortunate choice. You think of him as a statesman, but Franklin was actually was one of the premier scientists of his era. And he accidentally identified the charge on electrons as negative. He didn't know that about electrons. He just said that that's negative charge in reference to some particular situation, and what he was naming negative charge, and by doing that turned out to be electrons. Anyway, they're little negatively charged particles, and it's a nuisance because they're the carriers of electricity, and they're all negatively charged. It's like dollar bills all printed in negative denominations. Anyhow, electrons carry electricity in most circumstances. They also carry heat in most metals. And how does that go on? Well, if you look at the rod that I was waving my hands about a minute ago, if that rod is made of glass or wood or chalk, the bucket brigade process is the principal way in which heat is flowing. In a metal, there are charged particles, electrons, that can move long distances. And that's how they carry electricity. They move between atoms. In fact, they can move significant distances before they bump into anything. So they're sort of kind of like free-range particles. And they can carry heat nicely. So they pick up heat at the hot end. And instead of passing it to the next adjacent atom, they travel 100 atoms or 1,000 atoms across and drop it off when they collide with something. So suddenly the heat is taking giant steps from the hot end to the cold end by huge leaps. And suddenly you've got a material that can carry heat much more effectively. And this is why the metals, you know this from experience, that you can stick a wooden spoon or something like that into boiling water and stir all you like, and you're never going to burn your hand. But you do the same thing with an aluminum spoon or a copper spoon, or to an extent even other metals. We'll talk about that in a minute. You will burn your hand. The heat flows much faster, carried primarily by the electrons that are making these giant leaps through the material. Is that okay? Even within the metals, and that's when now I should get this started before, because it takes a little while, to show you about metals, because, yeah, you should know a little bit about metals and heat flow. It's not only it's important to the problem set, but it's important to life. It's just, this is part of living in the real world, which is the purpose of this class, apart from, yeah. This structure here has a central hub that I'm going to heat with a burner. And attached to that hub are 3 spokes that go out, and they are made of 3 different metals. And, boy, copper I can tell. This is copper. And secretly, copper of the 3 metals, this is the one that conducts heat the best. It's the best electrical conductor of the 3. It's also the best thermal conductor of the 3. The other 2, which are really they fake me out after a while. I can't. Stainless steel is one of them, and the other is aluminum. And if I could have them play with in my hand, I can tell you which one's which pretty easily. They have been burned and cooked to the point where they're kind of by eyeball. I think that one's aluminum, I think that one's stainless, but I wouldn't bet big money on it. So the point is, I'm going to heat the central hub. And hanging from those 3 spokes are a bunch of marbles, metal marbles on putty. And the putty will get hot and melt. You know, it could be wax. And so we'll see how fast heat flows, is conducted out these spokes. And what I'll predict is copper is the best of the bunch. It will conduct heat out and melt the last one reasonably quickly. Aluminum is a close second. So aluminum turns out to be a pretty good conductor of electricity and a pretty good conductor of heat. Stainless steel is a rotten conductor of both electricity and heat. You know, stainless steel is great as far as like avoiding rusting and staining and all that stuff. As a conductor of heat, not so good. And certainly not as a good conductor of electricity. It's, you don't get something for nothing, and stainless steel is imperfect. Actually, it's imperfect for the same reason, for an interesting reason. The pure metals, copper and aluminum, these are both fairly close to being pure metals. They're not truly pure metals in these contexts because pure metals are relatively soft. So these are just things that you ought to know. Pure gold. You know, why do people go like bite, the cartoon characters biting a piece of gold? If it's genuinely pure gold, nothing else in there, it's pretty soft because the pure metals are metals are crystalline with very rare exception. Very exotic materials are non-crystal, but they're crystalline. And if you've got pure crystals, the crystals can deform pretty easily by sliding layers of atoms across each other, particularly the metals, a phenomenon known as slip. Something, well, anyway, it's interesting to know that in these beautiful pure metals, one element just by itself it's pretty easy to get layers of atoms in these beautiful latticework arrangements to slide across each other. The details we could get into, but I won't. And so pure materials are pretty soft. But on the other hand, because they're pure, electrons can often travel long distances through them without bumping into any funny structures. When you start mixing the elements together, make alloys, then the lattice work isn't so simple. And two things happen. The material gets harder, and the electrical conductivity gets worse, because the electrons start hitting the transition areas from one metal to the other. So this is the origin of the early metals that people had to work with, are things like copper. Like you make tools out of copper. Yeah, you got tools that are metal, but they're not very strong. They're too soft. So what do? Make alloys like bronze and brass, both of which are alloys. And they're much harder. They're not as good at conducting electricity, but they're harder to bend, because the slip, you can't get that slip when you've got all this erratic stuff going on. So that said, the copper is pretty nearly pure copper. The best conductors of electricity and of heat are truly pure copper, but that's pretty soft stuff too. So we use it. We use it, and you can get a bar of copper that's like this thick, and you can just bend it like it's chewing gum. Pretty fun. For structural reasons, most copper is alloyed a bit, so it has some strength. It comes at the cost of thermal conductivity and electrical conductivity. Aluminum, same thing. Pretty nearly pure, but not 100% pure, too soft. Stainless steel, it's an alloy completely. It is iron, chromium, and nickel. It's a mess structurally inside that gives it wonderful corrosion resistance and so on, but it's not good. It can be reasonably hard, but you can still beat it with pure. You can beat it with steel, which is another iron alloy. But stainless steel is crummy as an electrical conductor and thermal conductor because it's just such a messed up alloy. Is that okay? I mean, I'm sweeping details under the rug, but it's pretty good. Okay, let me start this thing. And we can have a sort of a horse race between the three spokes. All right, so this will cook away. Heat is now going, it's going by bucket brigade, but it's going especially fast in the good conductors of electricity, copper and aluminum. And I want to make sure I give everybody a fair shot here. Okay, it's cooking pretty decently. You okay with thermal conductivity, thermal conduction? I should mention that in the lecture video, and I'll tell you here too, that gases are particularly bad thermal conductors. If you can keep the gas from flowing, so you keep it in place, it's got a terrible, first of all, gases are not electrical conductors. Normal gases are not. So they don't have the metal's opportunity to move heat by way of electrons. But they're also terrible at the bucket brigade trick. So the heat flows very badly through gases. And as a sort of this is to foreshadow the fact the best insulator, that is the worst thermal conductor, the best insulator that we have in general for clothing, to keep us warm in the cold weather, to keep us cool in the warm weather. And copper and aluminum just lost their marbles, their first two marbles. The best insulator we have in general is air. So to give away the secret of clothing and insulation, most of the insulation we use are air-based. You're wearing clothes to keep you warm in your coats and all that. The primary insulator in those coats is not like the down or the cloth. The purpose of the down and the cloth is just to keep the air from moving, so the air can be the insulator. So is that okay? Hair, same thing. What's your hair's job? Your hair isn't a great insulator. It's okay. But the air trapped by your hair is a great insulator. All right? Convection. So while conduction is conducting over there, another way heat can flow into the room from the wood stove is by convection. So conduction will get heat to the outer surface of the wood stove. Now we got to move it into the room. and copper lost its second marble. It's distracting. And aluminum is trying to catch up. Okay, and you notice stainless steel is kind of like, is it hot in here? It's terrible. Just to continue with this before I go into convection, is like, this is a lot about cooking. So whether I give away answers on problem sets, who cares really? When you guys, if you cook and you do something slightly more sophisticated than Easy Mac or ramen, right? You get a pot, you put it on the stove, and there are things that can happen. Like if you've got an electric stove with the spiral burner, it just, this thing that gets red hot, right? That's the spiral. If you put a thin pot that is a poor thermal conductor on it, such as a cheap stainless steel pot, you can get that same spiral to appear in the stainless steel. You put the pot on the burner, it gets hot where it touches. It is such a crummy conductor of thermal energy that the parts that are between spirals on the burner don't get hot. So you end up heating only the parts that you're touching, and you can essentially see the burner right through the stainless steel. It just mimics the burner. Is that okay? And now you want to cook in that, and you expect to have uniform temperature on your food? No, you'll get hot spots on the food where the burner is, and you'll get cold spots where the burner isn't. So a cheap pot made of stainless steel, which is a crummy conductor of heat, tends to burn food. You burn it where the burner hits, and you don't cook it where the burner doesn't hit. Is that okay? On the other hand, stainless steel is nice for the handles of a pot because it's a crummy conductor of heat. So the pot can get hot, but without burning your hand, because you're grabbing a stainless steel handle that doesn't conduct heat well. So pots made out of stainless steel, if that's the stainless steel is fine as the insulating parts of the pot, the handle. It's not so great as the heat conducting parts of the pot, the body of the pot. What do? Well, that means that most good pots are either made of thicker metal, because the thicker the metal is, the more pathway there is for the heat to flow. They're either made of thicker stainless, which is still not quite the ideal, or they're made of better thermal conductors like aluminum or copper. The problem with aluminum or copper is they're not quite as easy to clean or non-stick as stainless steel. So even the fanciest of the pots will have a good thermal conductor hidden inside stainless steel. So you probably have encountered those pots from time to time. Maybe you have them. Pots that are laminated. They have a copper or aluminum core to carry the heat around nicely, so you don't scorch your food in one spot and not cook it in the other. But they have stainless steel on the outside so you can keep them clean and sweet. Is that okay? So anyway, there's physics behind. And at this point, aluminum and copper are done, and stainless steel is just nothing. All right, so I hope that's convincing. Stainless steel, interesting is it shows up all over the place in cookware, but be aware that it's not good for conducting heat. Let me do an extreme case of that, and that's, I guess I can turn this one off. Here's a burner over here. Okay, so it's a more aggressive burner. If this were a rod of copper, and I did this, I would burn my hand in 3 seconds. It's not a rod of copper, it's stainless steel. And furthermore, it's hollow. It's a stainless steel tube. So this is such a crummy conductor of heat that I can heat that end literally red hot. Can you see it glowing? Right? I can heat it red hot and I feel nothing. I'm emotionally stunted. I don't feel anything. All right. Anyway, no problem, because the thermal conductivity of the skin is so crummy. No problem. All right? So it's good for handles, not for cookware. Okay. Moving right along slowly. convection. Once you get the heat onto the surface of the wood stove, you want to get it into the room. There are going to be two ways it gets into the room. One of them is convection. The other one is thermal radiation, which that glowing red that I just showed you, that's not unrelated to heat transfer. That is heat transfer, but we'll come to that in a minute. So convection is when you heat up a fluid. I guess in principle it could be anything that moves, so it could be marbles. You heat up a fluid, and then let the fluid carry its thermal energy somewhere else. And that thermal energy moving with the fluid can be described or be defined as heat. You know, it's thermal energy moving from one place to another. Well, that's heat. And that's one of the primary ways in which heat flows out of the room from a wood stove. When the wood stove heats the local air up, that air now has thermal energy in it, and if it moves, it carries thermal energy. Well, it does move because hot air is buoyant. We've already seen that and why that's true. It's when you heat air up and leave its pressure unchanged, which is what happens when I just turn on a burner there, the air above the burner heats up. It has to stay at atmospheric pressure because if its pressure rose, it would accelerate toward lower pressure and spread out. So the pressure around a wood stove starts at atmospheric pressure and stays at atmospheric pressure the whole time. Is that okay? But the gas making up the hot air that is now at atmospheric pressure has to be low density because it's hot, because its temperature is high, the atoms and molecules that are in the air are traveling harder, hitting more often. Each one contributes more to pressure, so you need fewer of them per liter. So the bottom line is the density of the air drops around the wood stove. It is hot air at low density. It is therefore buoyant. It's pushed up harder by the buoyant force of the air around it than its own weight. So it has a net upward force on it. And it rises just like a hot air balloon. Yeah, hot air balloon's got a skin around it, an envelope, and you can say, there, it's a balloon, up it's going. But that's true of just air itself. If you just heat a blob of air in the middle of air, the blob of hot air, which is going to have low density, is now pushed up harder by the buoyant force than its weight, and up it goes. Doesn't matter that it doesn't have a skin. It's not important. It goes up anyway. And it starts creating what are known as convection cells. So that the air rises off the wood stove, goes up to the ceiling, obviously can't go any further, so it begins to spread out across the ceiling, and as it does, the flow of air up, it has to be replaced by something else. So air flows in across the floor and rises up to replace it in the wood stove. So you got air spreading out, rising and spreading out on the ceiling, and moving inward on the floor to replace the rising air. And finally, that process it closes on itself. The air going up to the ceiling actually then begins to descend around the walls toward the floor, and then goes back in past the wood stove to pick up more heat. So it makes cells, cycles, over and over, like that. And you can see these, and what I'm going to do is I'm going to project them on the screen the old-fashioned way with a projector. You know, this was life when I was a kid, none of this TV screen stuff. I am going to turn off the side camera and turn down the lights. How far down can we go? Is that enough? Yes. Okay, so what you're seeing projected up here is a filament that we can heat electrically. And this is water in here. You're looking through a glass cell here full of water. There's the fill line right there. Not very distinct, but it's there. And we're going to heat up the water electrically like this. And what I want you to see is you can see the striations rising, hopefully, rising up here. This is heated water, which, like heated air, is buoyant in ordinary water. The water expands a little, and up it goes. It rises up here, and then it spreads out. And that battery doesn't look like it's at peak charge. We're not getting quite as strong flow as I'm used to seeing. Anyway, it's definitely going up here. It should be spreading out on the top surface. Actually, this line I see here is evidently not the end of the water. The water is going all the way up to there. And it's hard to see if anything is coming down on the sides, but it should be coming down on the sides. All right, I'll stop this. Come back to. So you're okay with the idea that you get convection off of a heated surface? Actually, you've seen this. You turn on the stove, whether it's an electric stove or a gas stove, you put your hands far from the burners, off to the side, nothing. There's not much going on. You go right over the burner, oh, it's hot, because you're feeling the hot air rising off the burner. Is that okay? Public service announcement aspects of the convection coming off a wood stove. The heat's going up to the ceiling, and it's spreading out on the ceiling. And it's nice and toasty warm up there. And so if you have a mezzanine level or something like that in your house that's up there, great, you're going to be nice and warm up there. But down here on the floor, you're not in the hot air. I mean, you have to wait for the hot air to accumulate up there, and maybe some of it will come back down once there's enough. But ideally, you would do something to get the hot air to come down to you if you've got a tall ceiling. Particularly if you've got a great room with two stories of open space above the wood stove. All the hot air is up at the ceiling. So put in a ceiling fan. Is the purpose of a purpose of the ceiling fan is to blow the hot air down during the winter. So you turn it on so you can run the ceiling fan both directions, but the direction in which it blows the air down is probably the most effective way in this situation to heat the whole room, not just the ceiling. Is that all right? Incidentally, the simple name for the rising heat off the wood stove, spreading out in the ceiling and come back down, that's just natural convection. It occurs because hot air is buoyant in cold air, right? So natural convection is a subset of all possible convections. The other type of convection is forced convection, which is what happens when you flip on the ceiling fan. Now you're not waiting for buoyancy to move the air around according to its whims. You're deliberately stirring the air mechanically. So that's forced convection. And having said that, coming back to cooking again, stoves, many modern stoves have two choices. You can just turn on baking, or you make the oven. I'm really talking about the oven. You can make the oven hot, and that involves natural convection. So there's a natural convection going on, and I'll leave that to the problem set to an extent. The alternative is to switch on the convection oven. Well, that's a misnomer. It's not literally a convection oven. Any oven is a convection oven. Convection's going on pretty much in any oven. This is a forced convection setting. So when you turn on the convection oven, you're turning on a fan. You're forcing the convection. And it's like turning on the ceiling fan. Now you're not waiting for buoyancy, natural buoyancy to stir the air around. You're just whizzing it everywhere. All right? That's part of getting the heat out of the wood stove into the room. Second part, the most sophisticated, well, I don't know, complicated or mysterious, I guess is still. I said that gases are bad thermal conductors. Does air count in that as well? And the answer is yes. Air is a terrible thermal conductor. But if you can get the air hot by bringing it into very close proximity with a hot surface, like the wood stove, the air is now hot. And if you kept it where it is, it would stay hot and no heat would go into the room. This would be terrible. So if you put a blanket around the wood stove to trap the air, you'll get the air hot and it'll sit there and it'll play insulator, assisted by the blanket, and you won't heat the room well at all. But if you allow the air to move, having picked up heat, you now move the air over and bring it, say, to your skin. Oh, it's hot. So you've skipped the conduction process and going right to the convection process. Actually, you know this kind of thing too. You go swimming. Actually, well, water's a terrible conductor. Air's a terrible conductor. let me stick with air for the moment, that if it's really cold, if you step out in really cold weather and there's no wind and you just stand really still, you can warm up the air very close to your skin. With a little luck, you can keep it from moving. If you got a little hair maybe to keep it from moving, and you can start to feel warm. But if you start moving around, or if there's a wind to blow away the air that you've heated up, it feels much colder, because now all of a sudden you have to heat new air up. So the key point here is that convection can move heat pretty well, even with a material that's not a good conductor of heat. Water is not a good conductor of heat. And this is another experience that you know that you go into the cold water you go into the pool and it's way too cold. If you just stand really still, you heat up the water right near your skin, and yeah, it's convecting a little bit, but if you can just sort of keep it motionless, after a while you feel comfortable. But then as soon as you start moving, it gets cold again. Hopefully that's familiar to people. It's okay? Radiation. Let me talk a bit about radiation. The other way in which heat can move from a hot place to a cold place is by way of radiation. And the radiation they're talking about here is electromagnetic waves. What's an electromagnetic wave? It is a disturbance in space that involves electric and magnetic. The influences that push on electric charges and magnetic poles. So you've seen static electricity, whether you've taken the other class or not. You know that there is such thing as static electricity, and that there's sort of electric charge can push on stuff. And you know, certainly play with magnets, and you know that magnets can push on each other. The influence that they use to affect each other, the charges used to affect other charges and magnets used to affect other magnets, they're electric and magnetic. They're called fields, and I don't want to go into the detail of the electromagnetic fields. But that influence, those influences, the electric influence, the magnetic influence, as a team can travel across space carrying energy with them. They travel as a wave, as a ripple. It's called an electromagnetic wave, and we see electromagnetic waves literally with our eyes. What you're using right now in seeing me up here is you're seeing electromagnetic waves that originated in these lights, bounced off me. Some of them were absorbed by me, and some of them weren't, and some of them go flying back around the room, and you're seeing them whiz along through the room. Now the ones that we're seeing with are not associated with thermal energy, so they're just independent of that. But it turns out that electromagnetic waves can be produced any time an electric charge accelerates. So if you take an electric charge, or you grip one, suppose this is an electric charge, or this is electrically charged. If it's sitting there motionless, no electromagnetic wave. If it's moving at constant velocity, in principle, it's a little oversimplified, but no electromagnetic wave. But if I shake it up and down, now I create an electromagnetic wave, a ripple. It's like bouncing your hand up and down in water. That's what you got to do to make a ripple on the surface of water, is go up and down. It's not unrelated. Anyway, so the point is this, that a hot object surely has electric charges in it. We're all made of electrically charged stuff. And thermal energy causes the charged particles from which everything is made to jiggle around with thermal energy, which involves a lot of random accelerations. The hotter something is, the more ferocious those accelerations become, because the more fierce the jiggling is. So if you've got jiggling charged particles, they're going to launch electromagnetic waves, and they do. So when you're looking at sunlight, what are you looking at? You're looking at waves that were launched from the effective surface of the sun. The sun actually does have a surface. It's not a hard surface that you can go and tap on, knock anybody there. But it's photosphere. It's a certain layer of the sun that is really where the light comes from. And it's quite hot, like almost 6,000 Kelvin, which is vicinity of 11,000 degrees Fahrenheit. Pretty hot. It's got lots of charged particles in that photosphere. They are jiggling around fiercely, and they are launching all their little electromagnetic waves. Off they go. All right? Everything that has thermal energy, which is to say everything, because everything's got thermal energy, everything has thermal energy and it has charged particles, everything's emitting electromagnetic waves. The spectrum and brightness of the electromagnetic waves depends on temperature. But you guys are glowing. The room's glowing. Everything is emitting electromagnetic waves. And the hotter something is, to bring up characteristics that I haven't talked about before, electromagnetic waves can be the spectrum of electromagnetic waves extends from radio waves at the low frequency, long wavelength end. So low frequency meaning that the wave undulates up and, it's not in space, but it's pointing up and down. The electric influence is going back and forth and back and forth. Charged particle up, charged particle down, charged particle up, point up, down, up, down, up. It's doing it slowly. That's low frequency. And the wave that it sends out in space undulates slowly in space, long wavelength. That's radio waves. It goes all the way through the visible spectrum, which we're using to see each other right now, off into the very high frequency, short wavelength world of X-rays and gamma rays. So it's a whole swath of possibilities that subsumes a bunch of phenomena that you hear tell of, like radio waves, microwaves, infrared light, ultraviolet light, well, visible, of course, X-rays and gamma rays. The point is here, the hotter something is, first off, the brighter it becomes, which is to say the more power it radiates, the brighter it becomes. And also the frequency of its average wave gets shorter. Gets higher. The wavelength gets shorter. So a very cold object concentrates on emitting radio waves and microwaves, which we can't see at all. A somewhat hotter object begins to concentrate in the infrared, which we still can't see, but you can start to feel it. Hotter still, and it starts to include some of the visible, like the red end of the spectrum, which you were seeing when I was heating up that piece of stainless steel. I got to the point where it was glowing cherry red. Well, that's a certain temperature. It's starting to emit part of the visible spectrum, but the red end. If I got it still hotter, which is going to get hard, it'll start going deeper into the visible, and it'll start to include yellows and even greens. And you go hotter still, and you start getting the blues and the violets, and then you get the color of the sun. And then in principle, you can keep on going and get into the X-rays. So what I want you to appreciate at this point is that everything is glowing right now, emitting thermal radiation. That includes things at room temperature. It's just not very bright, and it's in the parts of the electromagnetic spectrum we cannot see with our eyes. Machines can see it, gadgets can see it, but we can't see it. If you get hot enough, it gets both bright enough, and then certainly it gets into the range of the electromagnetic spectrum that our eyes can see. And so now it includes visible light. And the exchange of heat that occurs in this context goes by these electromagnetic waves. It's always two-way. At least the microscopic exchange of thermal energy is both directions. That is, you are radiating thermal radiation to everything around you, and everything around you is radiating thermal radiation toward you. It's both ways. The only issue is who's hotter. If you're hotter than your surroundings, you will be brighter and emitting more thermal radiation than your surroundings are sending toward you. So the exchange is, you dominate the exchange by giving away more thermal energy than you receive. And heat flows from you, the hotter thing, to the surroundings which are cooler. Let me show you before I just let this go forever. I'll do two parts to this. Let me just transfer thermal energy. First demonstration is transfer thermal energy from a very hot electric filament we're going to have over here, old-fashioned bulb. it's a 500 watt bulb, you can imagine. It's dazzlingly bright. We're going to collect the thermal radiation coming off of it, which is not entirely visible, but includes a lot of visible, send it across the room to that other reflector over there where it's going to be focused on a match. And to see the match, preset 1. Oh, I must have blanked the camera off. Side source is camera. There. You're looking at the match. It looks like it's already burned. That's actually magic marker on an unburned match. So it's now a good, black is the best absorber of light. It's also the best emitter light, which we'll come to. But we're going to send thermal radiation toward it and make sure that it's very good at exchanging thermal radiation, so it's been blackened. So I'm going to turn the light on, and it'll be dazzling up here. Hopefully you'll be able to see the match reasonably well. It's now got thermal radiation from my side of the room focused on it. And we're transferring heat from hot to cold. It's smoking, but it hasn't lit. Or maybe it has lit. How would you tell? It hasn't lit. Oh, there we go. Yeah, so we lit a match the really hard way with thermal radiation. All right. It's fun, yay. What I'll do here, I want to show you here, this is a device called a bolometer that sees thermal radiation. And next time, if I can pull this off, I'll bring some other devices that see thermal radiation. It's observing the thermal radiation coming off of a cube over here that's just being heated by a light bulb. It's got a light bulb inside, so it's warm. And the cube, the surface that we're working with looks black. And black looks like, black means no light, right? Nothing, nothing, nothing. What black means, a black surface is as good as possible at absorbing electromagnetic waves. It also turns out to be as good as possible at emitting thermal radiation. So dark things are good at absorbing light. They're also good at emitting light of their own thermal radiation. So this is that black surface is very good at glowing. If I use, instead of a black surface, a shiny surface, which is terrible at emitting thermal radiation, this bar graph should be showing us how bright the thermal radiation is. It's not very convincing today. This is the black surface, which is very good. The shiny surface is very bad. The worst source of thermal radiation I can think of is a very cold surface. The usual, any excuse, okay, this will do. So I want a really bad emitter of thermal radiation. I'm going to actually dip the glove. Whoa! I want to make a really cold glove. I'm not going to wear it, though. I predict that it's, did it go down? Yay! So it's a terrible emitter of thermal radiation because it's cold. So this surface, and you might think, you can't see that it's cold. You actually can. I mean, if your eyes were capable of it, you would see this is very dimly glowing as opposed to everything else around here, which is glowing much more brightly. So cold surfaces are cold. As a case in which you know this to some extent is when you go walking up to the freezing compartment of your, maybe it's a walk-in freezer or something. You open the freezer door, and you stand in front of it trying to decide which flavor of ice cream you're going to eat. You feel cold. Why do you feel cold? If it's been cooling the air and it's convection, the cool air is anti-buoyant. It goes down, and it cools your tootsies, okay? If it's conduction, you'd be touching it, but you're not touching it. So why are you feeling cold? It's because you are glowing brightly with thermal radiation of your own production. It's glowing very dimly because it's so cold, it's not emitting very much thermal radiation. So in this exchange between you glowing at it and it barely glowing at you, you lose. There's a net flow of heat from you to the freezer because it's just barely glowing. And you feel cold as a result. All right, we'll continue this kind of stuff on Wednesday.